All right. I guess let's begin. All right. So welcome to Chem A11 Experiment 2, Equilibriums and Le Chatelier's Principle. Just so you're all aware, this lecture will be posted, like a recording of this will be posted on Blackboard. So we will be recorded, is what I mean to say. That being said, I just want to let you guys know that I'm very, very sorry, but I've been TAing for a couple of weeks now, and I found that my internet and Blackboard just don't get along at all. And so I'm not sure if I told you guys this last week or not, but so if you could very please not open your mics or your cameras throughout the presentation. I am super sorry, but it makes my screen lag and the presentation starts to lag, and then I get cut off sometimes too. So just to avoid some of those things, that would be fantastic. I have put my email up here. Please write it down. Anytime you have a question, please feel free to email me. I'll answer everything on email. I will also be available after the presentation, after the first part of the lab. So in case you guys have any questions by email or by chat, email is preferred, to be honest, than chat, but whatever works for you guys. All right, so let's begin. Number 1, so organization of the lab. So we discussed this actually last week as well, but I just wanted to mention it again as some students were confused. So before the lab, your pre-lab quizzes are due. Then the first hour of your lab, so will be the lab talk, theory, practice, calculations. That's this portion that we're doing together. Then in the second hour, you will all be doing the Labster virtual lab. To be very honest, a lot of you guys had Labster questions. I honestly have not done Labster before. This is the first time I've ever even heard of it, and I'm not actually doing it. So I will actually ask if you guys could kind of stay tuned. Like, even if you're done and you're just doing your Labster stuff, right? If you could just, keep on the chat, and if anyone needs help, maybe give them some guidance. That would be much appreciated. And of course, the third hour, I will be having my TA office hours, right? A couple of important points here are that you must finish your Labster lab within 3 hours. Notebook reports due in 2 weeks. Except experiment 5 due in 1 week, and so on. I think we covered this last time, so let's not belabor the point here. Alright, today's lab is super exciting. It's on equilibrium constants and Le Chatelier's principle. These are topics that I personally find very, very interesting, so I hope you guys will enjoy it too. Alright, so 3 learning objectives. Number 1, to develop a deeper understanding on the equilibrium constant and reaction quotient. Number 2, understanding and applying Le Chatelier's principle to solve a real-life problem. And number 3, to understand the Haber process to manufacture ammonia. So once you understand 1 and 2, 3 will just follow, and you'll see why. Alright, a couple of things. Introduction. All chemical reactions can go both forward and reverse, right? So we think of certain reactions as always occurring. And like a classic example of a chemical change versus a physical change is like frying an egg, right? You know how you were taught in high school, or I hope maybe you were taught, I don't even know if you were taught or not, but I was taught in high school that you can't unfry an egg, but you can, freeze water, right? So freezing water is a physical change, frying an egg is a chemical change, right? And that's kind of how we were taught about chemical reactions. Well, as usual, we were not taught the whole truth. It turns out all reactions do go in both forward and reverse directions, but the degree to which the products or the reactants are favored differs between each reaction. So, what do I mean by forward and reverse reactions? Let's say we have 2 reagents, A and B, and they react such that certain amount of A moles of A plus B moles of B will give us C moles of C and D moles of D. So A and B are reagents, C and D are products, right? So the forward reaction is when A, B react to give us C and D. The reverse reaction is when C and D react to give A and B. It doesn't always have to be react per se, it could be a degradation. right? Like maybe A and B combine to give you C, and then C breaks up into A and B again. That's also possible, right? So one important thing to note here is the reaction rates. Now that I'm here, it seems to be like if I put the reaction rate there, I think that would have been more clear. But anyway, so the forward reaction rate is going in this direction. The reverse reaction rate is going in the opposite direction. All right, so what happens at equilibrium, right? So at equilibrium, the forward and reverse reaction rates are identical, right? And the equation for that, so the equilibrium of concentrations, so Kc is equal to the concentration of one of the products to the exponent the number of moles times the concentration of the other product times the exponent number of moles. If there's a third product, you just multiply it by that as well, divided by the concentration of the first reagent to the exponent of its moles times the concentration of the second reagent to the exponent of its moles. Right? And this actually equals the forward reaction over the reverse reaction. And you can also obtain this just by, if you have this equation here, divide both sides by k minus 1 by the by k minus 1, then you get k1 over k minus 1 multiplied by a to the a times b to the b, then divide both sides by that, and then you end up with this equation here. Over here on the right hand side, I have the forward rates and the reverse rates of the reaction, right? So this just tells you what's happening with the rates. So let's say you have the forward rate and the reverse rate at equal rates. That just means the amounts are changing. It doesn't mean the amounts are the same. It just means the rate of change is the same, right? So it's like saying that I give you $1, right? And then you give that dollar to someone else, or not that dollar, and you give $1 to someone else, right? And so on. So you haven't, the net increase in your money hasn't changed. Okay, that made no sense. Here's another better example, I think, that I literally just thought of. Let's say you're renting an apartment, right? You get $500 to rent your apartment, and you know your bills, utilities, whatever, and rent all come out to $500 as well. So you make $500, you lose $500. At the first of each month, let's say you get $500 from working and whatever. And on the first of each month, you also give that $500 to your landlord, right? So at the end of the day, you got nothing. Nothing changed, right? Whatever you got in, you gave out. The amount of money you had in your bank remains the same, right? And in this case, 0, but you can have different numbers. You can have like 30 or something. Right? I hope that makes sense. There's a million different examples we can do. If you guys want, maybe we can discuss this over email or Zoom or something, if you guys need some more examples. Alright, so now that we know that K, described here, right, can be positive or negative, not negative, sorry, but it could be greater than 1 or less than 1 is what I meant to say, or equal to 1. What does it mean? Right? So basically, the equilibrium constant summarizes the reaction, right? If K is much greater than 1, right? Much less than 1. There we go. Yeah. Then the reactants are favored, right? If K is equal to 1, that means the reactants and products are equal, and if K is greater than 1, that means the products are favored. And why that makes sense is if we look at this equation that we have here. Right? If K is greater than 1, that means C times D to the exponents of their moles are greater than A times B to the exponent of their moles. Right? So if C times D is bigger, that means the products are favored. Right? It just makes sense. If K is less than 1, so meaning A and B are favored, that means you have a small number over a big number, like 1 divided by 10. You get a decimal number, right? But if you have if C and D give you 10 and A and B are 1, that means products are favored and you have a much higher number than 1. But if you have equal to 1, right, if it's exactly equal to 1, that means that the amounts are exactly the same. It doesn't mean that they're both necessarily 1, it just means that if you have 100 of one, you have 100 of the other. If you have 10 of one, you have 10 of the other. They're identical in terms of ratio. I hope that's clear. Alright, gas phase reactions. So, similar to concentration, you can also have equilibriums with gases. Now, generally speaking, okay, you can do the exact same equation for gases. You can have Kc and it just works, right? However, with gases, it's often convenient to talk about them in terms of their equilibrium pressures, so Kp, right? And Kp is equal to Kc times RT to the exponent change in moles, right? And so that's how you calculate it. So what is the change in moles? What is delta N? So delta N is the moles of the products subtracted by the moles, or the sum of the moles of the products subtracted by the sum of the moles of the reagents. And what that basically tells you is that if this reaction was to proceed in the forward direction, are you increasing the number of moles that are present or decreasing the number of moles that are present? And that's going to be very important, because if you increase and decrease pressure, what is pressure? That might be a question to start with. What is pressure? Pressure is basically the number of molecules pressing against a container, right? So the more molecules pressing against the container, the more pressure there'll be. And the more molecules means the more moles. So the greater the number of moles, the more pressure pressing against the container. So now, in terms of equilibrium, this will be valuable to us because we want to talk about things like what happens if we decrease the volume of a container. Well, if you decrease the volume, you increase the pressure, right? If you increase the pressure, that means that, and we'll talk about this later, equilibrium will shift to kind of compensate for that, right? So anyways, but if you have that the moles are equivalent, then N equals 0 and Kp equals Kc. Right? Because anything to the exponent 0 is 1. So if you have the same number of moles and the pressure is equal to the concentration, no problem about it. Right? Just something to keep in mind for the future. Alright, Le Chatelier's principle. So, Le Chatelier's principle states, for a system in equilibrium, if you change one of the variables, the equilibrium will shift to counteract that change. Basically, Le Chatelier's principle is telling us that equilibrium works like an annoying brother or sister, little brother and sister. You know how when you tell them to do something, they always do the opposite? Right? So, something like that. So, for example, if I increase the concentration of C, the equilibrium will shift to reduce C. And how does it reduce C? It'll favor the reagents A and B, right? So if I decrease B, like let's say I decrease a reagent, the equilibrium will shift to increase B, and therefore a shift towards reagents, right? So basically, Le Chatelier's principle states that the equilibrium always does the opposite of whatever you did, right? It's always playing the opposite game. That's how I think of it personally. I hope that works for you guys too. Alright, so let's say that a reaction has not yet reached equilibrium, right? So how do you know in which direction it will proceed? So let's say that we have a reaction that is not at equilibrium, right? So we know that certain reactions will reach equilibrium, and we know that once they've reached equilibrium, things won't change, and so you can just leave stuff for a really long time and then just measure it, and you know what it will eventually one day come out to, right? But what if you want to know where it is now and where it's going to be in the future, right? So what we do here is that we use something called the reaction quotient, and it's symbolized by Q, probably, and this is a theory of mine, that because, Q for quotient, that's what I think. To be honest, I don't even know if that's why the symbol Q was used. But anyway, what it is basically the exact same thing as K, but at the moment, right? So let's say that you know the value of K because someone did an experiment, lasted like 4 days, they let like two things react, and they measured the concentration after 4 days or whatever, right? To get the equilibrium. So now that guy has published, what the equilibrium constant for our reaction is. But we don't have that reaction in equilibrium, so let's see what happens. So what we do is we plug in the concentrations that we have now, and then we compare it to K, right? If Q is less than K, right, which means that, let's say K is 100, but Q is only 50. Well, that means that we need more products, right? Because Q has to increase to get to K. If Q increases, the only way for this to increase is if C and D increase, right? In ratio wise, A and B will decrease as C and D increase, right? The two are correlated, right? If this is the case, that means the products are going to be favored, right? But what happens if Q equals K? That means we're at equilibrium. Nothing is going to happen, right? It's going to be the most exciting experiment you're going to do. It's going to be exactly the same. Things aren't going to change. I mean, that might be useful though. That might be useful, right? And what happens if Q is greater than K? So let's say K is 100, but Q is 1,000. What does that tell us? That tells us C and D are about to decrease pretty big, and A and B are going to increase. What that means is that the reaction is shifting to the reagents, or shifting to the reverse, right? And so that's how Q and K are utilized. Do you guys have any questions? Okay, maybe I'll just kind of keep going. By the way, I forgot to mention, I'm actually on as Sayyid Ahmed number 2 as well, because I found that my phone, it doesn't lag when the presentation occurs, whereas the actual presentation itself, like if I try and type and do things on the computer while presenting, it tends to lag, but if I do it on my phone, it doesn't. That's why you'll see 2 Sayyid Ahmeds, and don't be confused. It's just, that's how it is. Right, and so I'll often be texting from my phone while we talk. But I'm texting you guys, by the way. Right? Awesome. So, temperature and equilibrium. Now, okay, so let's talk a little bit about what is an exothermic and endothermic reaction. So, an exothermic reaction is a reaction, in our case A plus B gives you C and D, which releases energy, which is symbolized as heat, as the delta triangle, as energy. Right? So that's an exothermic reaction. An endothermic reaction, in our A plus B gives you C and D, it's A plus B plus energy gives you C and D. Right? So what that basically means is that you can treat temperature or energy as a reagent, right? So just like if you increased, like in an exothermic reaction, let's say we increased temperature, what would happen? Well, the equilibrium would shift, away from the products, because temperature is a product of this reaction, right? So it'll shift towards the reagent. So for an exothermic reaction, heating it actually forces the reverse reaction. But an endothermic reaction, heating it actually drives it forward, right? Because if you heat it, you increase the temperature, you increase the reagents, you're going to get more products. I hope that's clear. Basically, what I'm trying to say is that the temperature works just like in a regular compound or regular reagent or product. Alright, volume and equilibrium. So another thing is volume. So volume is always paired with pressure, right? When you talk about volume, the volume itself doesn't do anything per se. It's the pressure that it causes that causes things to happen, right? And so when we talk about volume, we're inadvertently always also talking about pressure. Right? So, if gases increase in volume, they will thus increase in pressure. Right? So let's say that we had a gas that had, took up this much volume, right? But then, here's a fun one. For liquid nitrogen, right? So when you have liquid nitrogen and you have the cold gas, like nitrogen gas that comes off from there, right? And you take a look at that volume, when it's heated, expands like 230 times. So if you put that in a balloon, what do you think is going to happen to that balloon with 230 times more pressure being applied to it? It's going to pop, because what happens is that the molecules, as they increase in temperature, also increase in volume, which increases pressure. Right? And basically, with talking about pressure, if you increase the pressure, the equilibrium will shift towards the side with the least amount of moles. Okay? So, an increase in pressure goes towards less moles. But if you decrease the pressure, you go towards the side with more moles. Remember, everything's opposite here. If you're increasing pressure, right, you're decreasing moles. If you're going to decrease pressure, you're going to increase moles, right? So that's how it works. Any questions? Okay, I think we'll keep going on too. All right, so here's an example of the Haber-Bosch process, which is the synthesis of ammonia. This is a chemistry in real life. This is a real life chemical reaction used, right? So now no one can ever say, when are we going to use this in real life? Chemistry is all about real life, right? And so what the reaction is nitrogen gas plus hydrogen gas gives you ammonia, right? Plus energy, right? It's an exothermic reaction. Right? Just putting that out there. And the delta H of formation is 91.8 kilojoules per mole. Right, the standard enthalpy. All right, so it's actually used to make fertilizer now, but it has actually a very sad history. In World War II, it was used to make explosives during wars, so very sad. But nowadays, it's used for fertilizer, which makes more food, which helps a lot of people. So, good. It's redeemed itself. Right? It's done with a catalyst, and I should have a closed bracket here. Sorry about that. And the catalyst is usually iron, but uranium and ruthenium also work. But usually iron, cheap, easy to use iron. Like, who's going to want to buy uranium to make something, right? For it's just bad business trying to buy uranium to do business, unless you have nothing else that can work. All right. And then lastly, it's very easy to work with these sort of systems. So we didn't really talk about this when we talked about gases, but gases are super easy to work with. What happens is that if you remove gases, the equilibrium will always shift to create more of the gases. So for example, here, if you have nitrogen gas and hydrogen gas and you have them mix, right, to make ammonia, and then you have a filter, right? And that filter allows for ammonia to kind of be released by capturing the nitrogen and hydrogen. What's going to happen is that the ammonia will always be released, and therefore you're always decreasing the product, forcing equilibrium to go towards more, to make more and more product. The reaction will go to completion, right? Very interesting concept. It's super cool, super unique. But gases, by the way, aren't the only thing. Just fun facts for you guys. Strong acids and strong bases are also basically things that have very, very strong forward reactions. Right? So for example, HCl, very strong acid. Right? What happens is that the hydrogen and chlorine separate, and they separate very strongly, and the reaction goes to completion. I think like the amount is like 0.999% or something. Sorry, 99.99%. Like it's super, super close to 100%. Right? And sodium hydroxide is the same way. Alright, so let's talk about your pre-lab questions. So we had 3 lab questions that we're going to go over, and the first one is, what does it mean if K is much, much greater than 1? What does that mean? Right? Number 2, calculate the concentration, the equilibrium constant for concentration, not Kp, which is important to note, for concentration for nitrogen gas plus 3 moles of hydrogen gas gives you 1 mole of ammonia. Right? And we're given certain concentrations to work with. Right? And then how can we do that? The third question is, what effect will increasing volume of the reaction mixture have on the system? Right? And the system, what system? It's this system. Right? So hydrogen sulfide plus oxygen will give us water and, what is that, sulfate gas? I think it's sulfates. Sulfur dioxide gas. Right? And let's see what happens. Alright, the answer to the first question. Well, we know that, K is equal to products over reactants, right? And if K is greater, much, much greater, if K is greater than 1, let's talk about what if it's just greater than 1. Like, for example, 1.01 is greater than 1, right? So what does that mean? It means products are favored. If K is much, much greater than 1, so like if K is 1 billion, or 1,000, or 100, right? Okay, I realize I went down there, but basically what I mean is if it's much, much greater than 1, the products are heavily favored, right? Like, for example, the dissociation of, HCl breaks off into H plus Cl minus, right? It's going to be a huge K, right? Because the products are heavily favored. The dissociation, right, is heavily favored. Any questions about that? Maybe I'll give you guys a second. Alright then. I guess let's move on. If you have any more questions, you guys can feel free to just kind of email me, and that'll be great. Now the second question. So calculate the Kc for the following equation. N2 gas plus 3 hydrogen gas gives us 2 ammonia gas. Right? So if we know that the concentration of nitrogen gas is 1.5 molar, and we know that the concentration of hydrogen gas is 1.1 molar, and the concentration of ammonia gas is 0.47 molar, right? Then what we can simply do very easily is that we can take this forward. All we do is use our equation for Kc, and we'll notice that there's A plus B because there are 2 reagents, and 1 C because only 1 product. Now, if there was another product, then we'd have a D there as well, and if there's 2 more products, then we'd have D and E present. But since there's only 1 product, so we put C on top, right? And then we plug in the values. So we know that we have 0.47 as the concentration for ammonia to the exponent 2 because because there are 2 moles of ammonia being produced in the reaction. And we know it's 1.5 molar of N2, right? And to the exponent 1 because there's only 1 mole of nitrogen gas being used, and then 1.1 to the exponent 3 because of 3 moles of hydrogen gas. One thing to note that I think is particularly important is that we can only use Kc if the values are at equilibrium. If they're not at equilibrium, like let's say we didn't know where they were, then these values wouldn't give us Kc, they would give us Q. Right? Q and K are like exactly the same, calculated exactly the same way. The difference is just if K is always at equilibrium, Q is not always. Q is unknown. It could be or not be at equilibrium. And the light is kind of getting into my eyes. Alright, and next slide. Oops, skipped. There we go, here we go. So finally the last question. What effect will increasing the volume of the reaction mixture have on the system? So we know that our system is hydrogen sulfide plus oxygen gas. 2 hydrogen sulfides plus 3 oxygen gas is in equilibrium to give us 2 moles of water and 1 mole of sulfur dioxide, right? All of which are gases. So we know about volume. We know that if you're increasing the volume, that means you're decreasing the pressure, right? Like if we think of it this way, like we have our like let's say we have a container that has a certain moles, like say 4 moles of gas in it. Now, if you were to increase the volume of that container, the pressure that those gas molecules apply is going to decrease because now they have plenty of space to go in every direction. If you decrease the volume, then they're all congested and they're hitting each other and it's causing more pressure, right? So if you increase volume, you're decreasing pressure. And we know that from decreasing pressure, the equilibrium will always do the opposite. Right? So if we're decreasing pressure, equilibrium wants to increase pressure by going to the side that has the larger number of moles. Alright, so how do we know what side that is? So here we have delta N, which is the number of moles, or the difference in moles in products and reactants. Right? So we have the sum of the products, subtract the sum of the reactants. I was right the first time. Sorry, this is... Sorry, there is a slight mistake here. Let me fix that real quick. Give me 1 second, guys. 1 second. I goofed up a tad bit. Hopefully it doesn't cause too much damage. There you go. Oh, now my monitor turned off. Let me just turn my monitor back on. Alright, okay. Alright, there's my webcam again. So everything seems to be good. Sun's in my eyes. Everything's working great. Alright then. So what effect will increasing the volume have? So here, what the mistake I made previously was that, so you have the moles of the product subtract by the moles of the reactants. So we know that we have 2 plus 2 moles in the product, and we have 2 plus 3 moles in the reactants, right? That gives us 4 minus 5 and minus 1, which means that as we go from products to reactants, as we go from reactants to products, we are losing 1 mole of molecule overall, right? So if in the moles, like let's say there was no reaction, right? You just have 2 hydrogen sulfides for every 3 oxygen. You have a total of 5 moles of stuff in there per reaction, right? Whereas if it's 100% products, then you only have 4 moles of stuff per product. 4 moles of stuff, yeah, per product. Okay, I'm confusing myself now, so I'm just going to say it again one more time. Okay, if the reaction did not occur, then you have 5 moles of reactants. If the reaction is 100% completed, you would have only 4 moles of products. Right? So basically you're losing 1 mole, right? If you go from reactants to products. Now equilibrium, being that annoying little brother sister, always does the opposite. If the reaction is going to decrease, or if we're increasing the volume and decreasing the pressure, the equilibrium will try to increase the pressure, right? If it tries to increase the pressure, it'll go to the side that has the greater number of moles, which in this case is our reactants, right? So we have 5 moles in our reactants and only 4 moles in our products. So the equilibrium will shift to the left, right? I hope that's clear. I know I goofed up like 3 times in the words I'm saying, so I hope that's good though. Here. Cut. Can you guys hear me? Hello? Okay, I think we're back. I think I can. Yeah. Okay. Perfect. All right then. So thank you for listening, and I hope you guys learned a lot from this video. I'm very sorry for the internet connection and for the mistake I made. Totally sorry about that. And let me know if we have any questions. I'm going to turn off my webcam now because at this point I think it's just causing more problems than not. And it just keeps lagging. Okay, now my computer's frozen.